Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue talking about the revision of the probability for inshallah using all of what we remember now for the probabilistic reasoning session or Bayes-net session. So far we talked about the definitions of probabilistic modeling, joint distribution, marginal distribution, conditional distribution, events. Today, inshallah, we'll continue talking about probabilistic reasoning, and we start with probabilistic inference. Okay, so probabilistic inference means that we want to compute a desired probability from some known probabilities. So we are given some probabilities, given some values. Okay, so thanks for reminding me that I am not sharing the slides. I think you see it now. Okay, so probabilistic reasoning is about computing a specific probability given the values of the other variables. Okay, so usually we do it with when we have the joint distribution or conditional distribution, we want to compute another conditional distribution or a specific conditional probability. Okay, so we have known some values of variables, and we want from that we want to infer the probability of another variable. This is what we call probabilistic inference. Generally, we want to compute conditional probabilities because usually we are observing something in the real life or in reality or in the environment, and we want to infer something about a variable that we didn't observe yet. So for example, I want to know what is the probability of being on time to my work if there is no reported accidents. Okay, so I might infer the probability of 0.9 now, knowing that there is no reported accidents. So that constitutes my own belief. Okay, and I'm talking about now an AI agent, the belief of the agent about the phenomenon or the variable that I am interested in, which is being on time, given some evidence, given some observations. Now we call this the posterior probability. Okay, we have also prior probability, which is a probability without giving any evidence. Now this conditional probability might change with new evidence. So for example, if I know in that case, if I know that the time is 5 a.m., then the probability of being on time will increase to 0.95. Okay, so change with adding more evidence. Even if I have even more evidence, if I know that it's raining now, then the probability will drop to 0.8. So my belief or the agent's belief, okay, about some variables in the environment will change with more evidence. Okay, and that's what we call probabilistic inference. So our posterior probability will keep changing when we add new evidence or when we know some new observations. Now, how can we do this inference? We will start with what we call the brute force approach, which we call it inference by enumeration. Then, inshallah, starting next time, we'll see how we can do that efficiently. So here we will assume that we have the huge joint distribution, and from that joint distribution, we want to do some inference. What do we mean by that? We'll assume that we have n variables, and among these n variables, some of them are observed. We call them the evidence variables. Okay, what do we mean by observed? It means that we know their values already. Okay, so we call them evidence variables or observed variables. These are the variables E1 to EK here. Okay, so some of the variables are observed or evidence. Some of the variables also will be the variables that we are interested in, that we want to infer their probability. We call them the query variables. Usually they are one, but they can be more than one. Okay, so we call them Q or query variable. Now the rest of the variables we are not interested in, although they are modeled in our probabilistic modeling. We call them hidden variables. They are hidden because they are not observed, and they are not of interest now. But of course, they are part of the model, and they might affect the other variables, of course. Okay, so again, three types: evidence variables, query variable or variables, and hidden variables. So we are interested in computing probability of the query variable, okay, given the evidence variables. Given that we observe or we know the values of the evidence variables, I want to compute the probability of Q. Now this is generally is different from just the probability of Q by itself, which we call it the prior probability. Okay, so P of Q is the probability of the variable Q without knowing any evidence. Generally that's different, of course. Now knowing some evidence, our belief in Q might change. So to do that using inference by enumeration, we do it in 3 steps. In the first step, we select the interest from the joint distribution. Remember that we assume that we have the huge joint distribution table, okay, in which we have the probabilities for all combinations of values of the n variables. So the first step in doing the inference is to select the interest from the table that match the evidence or consistent with the evidence. Okay, so given the values of the evidence, we only keep the rows that are consistent with that evidence. Then we get rid of the hidden variables. How can we get rid of the hidden variables? By marginalization. Okay, so we sum out H, which are the hidden variables, to get the joint of query and evidence, to keep only the query and evidence variables. So for every value of the query variable, we sum out all possible values of H. That's exactly what we do in marginalization, as we did in the previous lecture. So this is like squeezing the variables that we have from the n variables to only the query and the evidence variables. Okay, so by that we get the joint sum of the joint subtable of the joint probability table that has the query and the observed values. How can we do that? Again, by summing over all the possible values of the hidden variables. Of course, we'll see an example, inshallah, in the next slide, but that's the main idea. After getting rid of the hidden variables, what we have now is this probability, okay? But these are not normalized, so we have to normalize them by dividing by the sum of their entries, which we call it Z here. So Z is the sum over P of Q and the hidden variables, okay, and we divide all the entries by that value, okay, because remember we want to get the hidden the conditional probability. So this conditional probability, okay, is the joint probability over the probability of the evidence. Okay, so we do this normalization step. So this is very similar to what we did in the normalization trick last time. Okay, the only difference here is that we have hidden variables, so we have to do the marginalization step in between. So the selection step and the normalization step, they were the 2 steps in the normalization trick last time. Now, because we have hidden variables, we have to get rid of them by marginalization. So we sum out the hidden variables in between, and then we eventually normalize. Let's see an example. Let's say that we have this joint distribution table among 3 variables: the season, the temperature, and the weather. And we have the probability for each combination of these 3 variables. Okay. Now I want to do inference, and I want to compute all of these 3 values. Let's start with the first one. I want to compute P of W. Now, we said that we have 3 types of variables, right? We have the query variable, we have the evidence variables that are observed, and we have also the hidden variables. with what we want to get here, we don't have any evidence variable, because we want to get the marginal probability of W without having any evidence. Okay, so we just skip the first step. Now the second step, what are the hidden variables? The hidden variables are the two remaining variables, right? So we have W here is the query variable, so that's the query, and these now are the sorry, not the evidence, the hidden variables. Okay, so these are H now. So we'll have to get rid of them by marginalization. Now, how can we do the marginalization? We sum over all possible values of H given specific value of W. So this is the row for sun, that's sun, sun, sun. So we will add up all of these probabilities. Okay, so that's 3.3, 0.4, 0.5, 0.65. So the probability of sun is 0.65 now. Okay, so that's getting rid of H. Now for rain, we add up all of these values. We should get 0.35 here. 0.5, 0.5, 0.05, 0.5, 0.1, 0.15, 0.35. Okay, so that's the probability of rain. Okay, so that's W, that's P, and that's the second step. Now the third step is to normalize. But since we didn't have any evidence, then the normalization will be useless. We'll just divide by the sum, which is already 1. So now this is the already marginal distribution that we need. Okay, so that's the prior distribution. That's the probability of W without any evidence. Let's do it when we have evidence. So probability of W given winter. Now we have the query Q, the query W is W, and the evidence is the winter, okay, which is the season. So that means that the hidden variables will be the remaining variables, which is the temperature. Okay, so the first step is to select all the rows that are consistent with the evidence, which is winter. Okay, so all the rows that are winter, which are these 4 rows, so we'll just cross out these rows. Then we get rid of the hidden variable T by summing over the values of W, the values of T. Okay, so for the same sun here, we have sun and hot, sun and cold. So we add these two values together. That will give us 0.25, and we add also these two values together because we have rain here. So this will give us 0.25 also. Okay, so the subtable now has sun 0.25 and rain 0.25 also. So the third step is to divide by the sum of these entries, which is the normalization. The sum here is 0.5, so that will give us 0.5, and so 0.25 divided by 0.5 is 0.5. The same here, so that will be 0.5. So you see that now the probability that we have a sunny day generally is 65%. Now, knowing that it is winter, it dropped to 0.5. Okay. Right. Now I want to compute this probability. Questions? Yusuf. Wa alaikum assalam wa rahmatullahi wa barakatuh. It is conditional probability. It is conditional probability. We are computing conditional probability here. actually conditional distribution. Okay, but this is the generalization of what we mentioned last time. Last time we had just 2 variables. Now we have n variables. So this method is called inference by enumeration. We look at the entire table and we do these steps. Okay, but still, of course, we are computing conditional probability. Okay, Yusuf, since you asked it, why don't you try with me the last one, if you don't mind? So we select the we select the 5th and 6th. So what are the evidence variables here? Winter and hot. The variables are, of course, yes, the season and the temperature. Okay, so winter and hot. So we keep these 4 rows, right? Sorry, not 4 rows. 5th and 6th, as you said. Sorry. So these 2 rows only, because they match the evidence, and we get rid of all the others. Okay, now we have this subtable. What's the second step? Yes. Yes, so okay, so the second step, usually we get rid of the hidden variables. What are the hidden variables here? No, the evidence variables are winter and hot. So these are the evidence. What is the hidden variable? The hidden variable is not there in the probability. We don't care about it. Which variables here we don't care about? So how many variables we have here? Yes, so we don't have any hidden variable here. So we'll just skip the second step. Second step is useless. Okay, we don't have any hidden variables. So we'll go to the third step, which is that's by what? Yes, what do we call that? Normalization. Okay, so we'll sum these values. This is 0.25. So we'll divide 0.1 with 0.25. Sorry, that's not 0.25. That's 0.15. Okay, yeah. So we'll divide 0.1 by 0.15 and 0.05 by 0.15. So eventually we'll get something like sun, which is, I think, 2/3, and rain, which is 1/3. So now this is the probability of W given winter and hot. So knowing that it's in winter and hot, the probability that we see a sunny day is 2/3, okay, which is getting up again after it was dropped to 0.5. Okay, so that's 0.67, actually even higher than the prior probability. Okay, thanks, Yusuf. Any question about this? Any question about inference by enumeration? So given the joint distribution table, we can compute any probability this way, any conditional probability or any even marginal probability, as you saw here. Okay, because marginal probability is a special case of a conditional probability given no evidence. Okay, the very first step is to determine what is the query variable, what is the evidence variables, what are the hidden variables, and then we do these 3 steps. As Yusuf indicated, this is generalization of what we did in the previous lecture when we did the normalization. In the previous lecture, we did it in 2 steps only, selection and normalization, because we didn't have any hidden variables. Here, it's a general case when we have hidden variables. We just do the marginalization in between. Any questions? Okay. Then we'll. So what is the problem of inference by enumeration? we have two obvious problems which are related, of course. The first one is that the time complexity is the order of the size of the table, which is, as we said last time, exponential, okay, d to the power n. So if we have 3 variables, we have 8 rows if d is 2, if it's binary. But as we add more variables and add as more values, as we have more values for the variables, that will be very huge and increase very quickly. And typically in real life applications, we have hundreds or thousands, sometimes millions of these variables. So that's really huge. And of course, if that's the case, then we have also to worry about the memory footprint of that, which is order of d to the power n also. So we'll have to find efficient ways, and that will be by factoring out this giant joint distribution table into smaller tables, okay? And by having these smaller tables, we have a strategy of getting whatever probability that we need from these smaller tables without the need of constructing the huge table. And we'll see that inshallah starting next lecture. Now let's continue our revision and let's talk about what we call the product rule. Last time we talked about the conditional probability rule, which is this one. Probability of x given y equals the joint probability x and y divided by the marginal probability of y. Now if you divide these two together, then we'll get the product rule. Okay, so probability of x and y equals probability of y times probability of x given y. What does that mean? That means that if I have the marginal distribution of y and I have the conditional distribution x given y, then by multiplying these together, we will get the joint distribution. And that will be really important when we talk about the more efficient way of dealing with probabilistic inference, which is base nets, inshallah, from next time. So keep that in mind. So this is like the marginal distribution. This is the conditional distribution. We can get out of that the joint distribution. Let's see an example. Let's say that we have two variables here, w and d, and we have the marginal distribution of w, and we have the conditional distribution probability of d given w. And we want from that, we want to get the joint distribution table. How can we do that? Now the joint distribution table will have, since we have binary values here, we'll have 4 rows. So for d and w, we have wet, dry, and for w we have sun, rain. Okay? Right. Now we want to compute all of these probabilities, the joint probability, not the conditional probability. So let's see how we can compute this one. So this is probability of wet and sunny, which is using the product rule. It is the probability of sunny times probability of wet. Let me write it. Of wet given sunny. It's easy, by the way, to remember because you can start by any of them and then do the conditional distribution given the first one. So you start by 1, then, so that's the probability of the first one times the probability of the second given the first. Okay? And the order doesn't matter, by the way. The order doesn't matter. And we'll see that inshallah in the next slide. So do we have these two probabilities? Yes, we have. Probability of sun is this value. So that's 0.8. And probability of wet given sun is this value, which is 0.1. So that's actually 0.08. Okay? How about this probability? Probability of dry and rain. So that's That's the product of the probability of rain times the probability of dry given rain. So that's 0.2 times 0.3, that will be 0.06. Okay? And so on. So you can compute these probabilities similarly. Is that a distribution? Is that a probability distribution? Yes. Yes, it is probability distribution. We don't need to do any normalization. Okay, because we just used the product rule. Clearly, we have the prior distribution of the first variable, and then we have the conditional distribution of the second given the first. Okay, so you see here the values 0.06, 0.08, and the rest are 0.72 and 0.14. Now, what if we have, instead of just two variables here, what if we have the joint distribution of n variables instead of 2? So let's say that we have 3. Now we can apply the product rule generally to get what we call the chain rule. The chain rule says that the joint probability of multiple variables is the probability of the first times the probability of the second given the first times the probability of the third given the first two. If we have a fourth one here, we would add probability of the fourth given the first three, and so on. Okay, that's why it's called the chain rule. So we order the variables in some arbitrary order, it doesn't matter, but just order them, and then we'll start by the first one, and then probability of the second given what we know already, which is x1, then the third given what we know already, 1 and 2, and then the fourth given what we know already, 1, 2, and 3, and so on. Okay, so generally we have this chain rule. If we have n variables, so that will be the multiplication of over I probability of xi given the previous variables x1 to xi minus 1. So if I is 1, we don't have anything, so it will be probability of x1. If I is 5, then it will be probability of x5 given x1 to x4. And remember, that's the multiplication of all of them. That's why it is the chain. It's a chain. Okay? Every term, with every new factor, we add a new term. So if you think about it, it is like observing the first, the joint distribution, the joint probability of n variables is equal to the probability of observing the first one times the probability of observing the second one given the first one times the probability of observing the third one given the what we know already, and so on. Time. Why is this always true? Why is this always true? So there is no approximation here. This is exact probability. Now let's look at P of x1, x2, and x3 here, what we saw here. So this is equal to P of x1 times P of x2 given x1 times P of x3 given x1 and x2, right? So what is this probability? By the product rule, this is P of x1 and x2, right? By the product rule that we saw in the previous slide. Now look at these two variables and these two variables, and let's think that they are one variable, x. Now we can apply the product rule again. Probability of x times probability of x3 given x capital, which is probability of x3 and x capital, which is x1 and x2, which is this probability. So you can do that multiple times, you get the joint distribution. So chain rule actually is not a new rule, it's just a generalization of the product rule over n variables. Product rule says that the joint probability of two variables is the probability of the first times the conditional probability of the second given the first. The chain rule just generalizing that on n variables by ordering them, probability of the first times the probability of the second given the first times the probability of the third given the first and second, and so on. Okay. Now, let's switch to the most important rule in probabilistic inference, which is called Bayes rule. So what is Bayes rule? Bayes rule is again not a new rule, but it's just readjusting the product rule. In the product rule, we say that P of x and y is equal to P of x given y times P of y. We can also order the variables in the reverse way, and that means that we can also write it that way. Probability of y given x times probability of x. So here we started with y, here we started with x. These are two ways of expressing the joint probability. Now, since these are two ways for expressing the joint probability, they are of course equal, and out of them, if we divide it by probability of y in the two sides, we will get Bayes rule. So what is Bayes rule? P of x given y equals to P of y given x. Notice that this is the reverse conditional probability times P of x divided by P of y. So given that we know this probability, we can compute the reverse conditional probability. So this is the conditional probability, probability of y given x, and from that we can compute the conditional probability, P of x given y, the reverse. Okay, both are conditional, but the beauty of the Bayes rule is that from one we can get the other. And that's, as I said, called Bayes rule due to its founder. Okay? Type. Why is that helpful? It is really very helpful because it's actually in reality, one of these two conditional probabilities is much easier to compute than the other. When it's much easier to compute, then we compute it, and hence we can compute the other from it. So let me give you an example. If I know that, so let's say that we have a symptom like fever. Okay, let's say that I have a fever, and I want to compute the probability that I have a specific disease, given that I have a fever, like migraine. Okay, the probability of having migraine. Okay, a specific disease, given I have a fever. Okay, so that's the symptom, and that's the cause, right? And usually we are interested in something like that. Given the symptoms, I want to infer something about the cause. I want to know what could be the cause behind that symptom. Okay, now that's not easy to get, but the easier maybe to know to compute the opposite, which is probability of the symptom given the cause. So in this case, if I have a migraine, maybe it's not a very good example. Let's say coronavirus. Okay, the cause is coronavirus. So what is the probability that I have a fever if I know that I have coronavirus? So I can compute that from those who tested positive, right? I can see how many of them got fever. That's easy. That's very easy. Okay, so we know this probability. But I'm more interested in the reverse probability, which is probability of having coronavirus given fever, given that I have a fever. Okay, now I can compute it using Bayes rule. So I have this, and I can now compute this easily. Okay, so this is exactly what I said in the previous slide, that the probability of the cause given the effect or the symptom equals to the probability of the effect given the cause, that's the reverse one, which is usually easier, times the marginal probabilities, which is also usually easy to compute. Example, if I have the disease meningitis, I think I pronounce it correctly, I hope, meningitis, and the symptom is stiff neck. Stiff neck is hard neck, I cannot move it easily. So this is a symptom now, so that's an effect, and that's a potential cause. Okay, now I can know the probability that I have the cause. I can also know the probability that I have the symptom given that I have this cause or in absence of that cause. And then I want to compute P of the cause, which is plus M here, given plus S. Okay? So I will have to stop here for the quiz, but I want you to think about how to do it. Given these three values, can I compute the probability that this person have this disease, given that he or she has this symptom? Okay, we'll do it together next time, inshallah, but I want you to do it before the lecture, inshallah.